We'll see. All right, so this was supposed to be a very dramatic introduction, and that's sort of spoiled now. Anyway, let's try it out anyway. So, rage. Goddess sing the rage of Peleus' son Achilles. Murderous doomed that cost the Achaeans countless losses. Now, these two verses are the introduction to the Iliad, which is an ancient Greek text that chronicles the siege of Troy. And if you've seen the movie with Brad Pitt called Troy, you sort of know what it's about. That's like 15, 20 years old now, but it's probably still the most widely known depiction of these events from modern times. So the Iliad was produced, ostensibly by Homer, who also produced another story called the Odyssey. And the Odyssey follows one of the Greeks that that was in the Iliad, his minor character in the Iliad. Once they were done, laying siege to Troy, he tried to get back home and he got lost on the way. So Homer produced an entire story about that as well. These stories are ancient. They go back to 1200 BC, so they're more than 3,000 years old. They're so ancient that if you read Plato, for example, and you read all the dialogues with Socrates and all of these people that Socrates discusses with, they often quote from the Iliad because it was considered classical literature already back in the 500s, 400s BC. So they go a long way back. Now, the Greeks were actually not the only people to produce ancient stories. The Persians had something called the Gilgamesh. The Indians have, Mahabharata. And I'm from Scandinavia. In Scandinavia, we have something called the Edda. So the Edda is sort of like, this chronicles all the Norse gods, and it's sort of like from the Viking age. So much more recent than the Iliad and the Odyssey. The Edda is only like 1,500 years old, maybe 1,000 years old. But apart from that, even though these ancient texts are, quite diverse in terms of origin, they actually do have one thing in common. They're all epic poems. And it's a little bit odd when you think about it. When I was a boy, I was interested in some of these things. I just liked science fiction and fantasy, and these things, the Iliad and the Odyssey and the Norse gods and so on. That looks like fantasy, doesn't it? So I was interested in it, but I was a little bit put off by this thing that they were epic poems. And I wondered, why are they actually epic poems? And I thought, first of all, as a boy, I thought, oh, it's probably just because, back in the old days, they liked poetry, and that was just their preference. But if you start to think about it, that can't really be the explanation, because there's thousands of years, the spans between the Iliad, something like the Edda. The Iliad is from, ancient, Bronze Age Greek culture, whereas the Edda is from the Viking age. So there's thousands of years, and it's a completely different region of Europe. So it's an odd coincidence if those disparate cultures would share a preference for poetry. And also share that preference with the ancient Persians and the ancient Indians and so on. So there's probably something else going on, and folkloristics sort of has the answer for that. So what you can imagine is that a long time ago something happened, some momentous event took place. That could be the siege of Troy. It turns out Troy is actually, was a real city placed in modern-day Turkey. So you can imagine that this happens, it actually does happen, and it happens, you have to imagine, well before anyone invents written language. So after this thing is over, let's just talk about the siege of Troy. After the siege of Troy is over, some of the soldiers come back home after the war, and they want to tell what happened to their family and friends and so on. So they retell all the events that they witnessed as well as they can. But this is just an oral retelling, so there's a lot of things that they probably don't get right. They forget some details. They probably invent some other details to make themselves look better. Maybe even if they were eyewitnesses to some of the battles, they may actually not have been eyewitnesses to specific events, so they're still just retelling what they heard other people talk about. Yeah, Achilles was actually hit by an arrow in the heel, can you imagine? And he died from that, and that might actually not have been true, but the guy who's retelling that story didn't actually see that, but he heard about it. And maybe he saw the body of Achilles after he was dead, or something like that. So the story gets retold and details get, changed and so on. And if the stories are compelling enough, later on the children and the grandchildren of the eyewitness will want to retell the story to their children and talk about, back when grandfather, was in the war with Troy and so on. And every time that retelling happens, the people who retell the story forget some of the details because they weren't there. This is just an oral tradition after all, so they're just telling the story as well as they can. And what probably happens is that, as the story gets told again and again and again, it sort of gets reduced to the essence of the actual story. So more and more details gets forgotten, and just the actual, skeleton of the story is all that remains. And the problem with that is that once you take away all the details, the story is actually not that compelling. No stories are compelling if you reduce them enough. You can say, all right, so one army lays siege to another, to a city. It takes a long time. Finally, they conquer the city. One of the soldiers, by the way, gets lost on his way home. I just retold you the Iliad and the Odyssey, and that wasn't particularly entertaining. But that's the essence of the story. So stories are alive with all the details, all the suspension of disbelief, all the comical interludes that might be there as well, and the narrative structure. And so if you forget about all of these things, these stories are probably just going to fade away, and they never really get retold because they're not compelling enough to be retold. So let's imagine someone else comes back from the war. And again, he tries to tell the story as well as he can, but for one reason or another, he decides to do it as a song. He wants to sing about his experiences as the siege of Troy. So he puts it in a song, and he rhymes, and he creates verses, and what that accomplishes is that it creates a structure to the narrative, so that whenever you sort of start to forget, oh, what comes next? Oh, it has to be something that rhymes with Achilles' heel. What rhymes with Achilles' heel? And you can sort of go from there. And that means that, people who want to retell the story afterwards, they probably add even more structure to the story, as it's being passed down in the generations. But it doesn't lose detail. It actually probably becomes more and more detailed. It changes, but it gets more and more, detailed. And it's not. I'm not saying it's a trivial undertaking to, learn by memory something like the Iliad and the Odyssey. There, if you write them down in like big books. But at least, this structure, the things have to rhyme, or that you have to follow some sort of alliteration, or that you have to follow, a specific stanza, so things like that. That aids memory, and it makes it possible for you to actually remember all of these things, and the story stays compelling that way. And this means this story gets retold and retold until it survives into an age where written language is actually invented, and someone then decides to write down the narrative, and at that point it's captured for posteriority. So this is probably why all the epic poems are actually poems. I don't think it was because they actually had a preference for poetry, but it's just like the poetry is a form that enables the content to survive. So it's almost like evolution, isn't it? You could say that epic poems are complex memes. And when I use the word meme here, I use the word in the same sense that Richard Dawkins uses it. So Richard Dawkins is the guy who came up with it. So I'm not talking about daft pictures with catchphrases on them. The idea of a meme is basically the same as a gene. A gene is a biological replicator, and if you have something like a shark gene, for example, the organism, according to the genetic view of the universe, the organism that survives is the gene, the shark gene, and the shark itself is just a vehicle that enables the gene to replicate and get transported into the future. So the gene is sort of like the perpetual, infinite life form there, and the shark is just the transport mechanism. It's a very efficient one. It's been around for a long time because it's very efficient, but it's not really the shark, it's the gene that's actually the real thing. And just like, a gene is a biological replicator being transported by, animals or by plants, then a meme is an idea that replicates, and the transport mechanism is the human brain. So there's a story into the Iliad, into the Odyssey, and all those other things, but the story would not have survived if not for the form. So we need that intersection between those two things. You know, you can have the world's best story, but if you can't remember how to retell it, it's going to fade away into obscurity. And you could have the most beautiful poem in the world that rhymes and all of that, but if it makes no sense, you're probably not going to keep on reciting it. This intersection between the story and the poem is what enables those epic poems to survive. So this is a very efficient organism for making sure that the story gets replicated into the future. And in general, we can say, you know, just like we looked at, you know, memes and genes, there's some content and there's some form that sort of needs to coexist there. If we're thinking about, you know, genetics, the genes are the contents; those are the replicators that we want to, you know, keep on, or that wants to keep on replicating. And the form is basically the animal or the plant that transports those genes across generations. So this seems like it's a general pattern, and I think it's a general pattern that also translates pretty well into software. You know, over the years, over the decades, there's been quite a few attempts at coming up with good metaphors for, you know, what is software development. And many decades ago, people would say, you know, software development, that's like building a house, which is pretty clear to us nowadays that it's not. And then some people came up with this metaphor and saying, you know, software development is like growing a garden, which is probably a better, you know, metaphor, but it's also faulty. But I thought about that, and I thought to myself, well, maybe software development is like writing an epic poem, because it seems like there's some similarities there. And let's not, you know, take this metaphor for more than it is, but I think it's worthwhile to just examine this idea a little bit. Now, so what I'm going to do here is I'm going to focus on code, and I'm going to talk about how code enables, you know, software to replicate as an organism. There's been plenty of people who talked about, you know, how to produce successful software. So I'm not really going to focus on that, but of course the software is important as well. I'm not the first person who gets this idea that, you know, genetics might, you know, provide some insights into software development. There's this article called The Self as Class, not The Self as Gene, but The Self as Class by Brian Foote and Joseph Yoder. And you can find it in this book, Pattern Languages of Program Design 3, but I think it's also online, just on the internet in general. So I'm not claiming that this is a new idea at all, but I think we can still, you know, expand on it. So the ancient Greek philosopher Polyrichus, as he said, you know, any fool can write code that a computer can understand. Good programmers write code that humans can understand. Now this is relevant exactly because, you know, we need code that a computer can understand in order to have working software. But in order to be able to replicate it and evolve it, we need, you know, to be able to change it. You know, code that a computer can understand looks like this. So what's that? It's assembly language, it's assembly code, and we're fortunate enough actually that there's a bit of code comments. So all the stuff that's you know, to the right there, those are actually code comments. And if it wasn't for the comments, we probably would be quite lost there. But there is there's a little bit of a hint towards the bottom of the screen there. It says, you know, if divisible by 3 and 5. Yeah, you can see that. I'm standing in front of it. So that gives you sort of a clue to what's going on here. We're looking at the assembly implementation of the Fizzbus Carter there. But it wouldn't really be particularly readable for us. But the computer can understand this. And then we'd say, well, okay, so if the computer can understand that, you know, we have working software, isn't that enough? And everyone knows that that's not enough. So this is why we're not writing in assembly code, because it's too damn difficult to write in. So you'd probably write the Fizzbus Carter like this. You'd say, okay, so let's just write, this isn't C#, but you know, the JavaScript version or the Java version or the C version would look fairly similar to that structure. And you say, okay, so that's why we're not writing in assembly, because it's too difficult to write in, but this is fine. Okay, this is a code that a computer can understand, and it gets the job done. And I say, yeah, but you actually did, whoever wrote this code, actually also, did something to the form of the code. Because why does the code look like this? Why are we not writing the code like this? Or why are we not writing the code like this? This would compile, it's the same code, it's just on one line with all the semicolons in between. And this compiles and does exactly the same thing. You can't tell the difference if you compile those different versions of the code. But we don't. We don't write the code like this for reasons that seem obvious, but still. We write code like this because it's easier to change. If requirements change, this is easier to make changes to. And that's what we want, if we think about software systems as, perpetual, evolutionary systems. Software always evolves. We always make changes to the software. We introduce new features, we fix defects and so on. So we want to be able to go and change the code. So again, we come back to this thing where the content is the software we want to deliver, but the form is the vehicle that enables us to actually move from one version of the software to the next version. We can't do that without the code, and we need to sit in that intersection between the content and the form in order for that to happen. So again, I'm going to focus on the form for most of this talk here today, because other people have talked about how to produce working software. So here's code, and you're not supposed to be able to actually read the code, because it's quite small, then the letters are quite small. But it's just to show you that here's some code with some structure. And what we see here is an example of something called the arrow code anti-pattern, or the code smell. You're not really supposed to structure code in that way, where it's sort of like the indentation just keeps on going to the right. It's almost like those arrows are pushing it towards the right. So what often produces this shape is if you have lots of nested conditionals, an if within an if within an if within an if within an if. And that makes the code difficult to reason about. So if you were Kevin Hennitz's talk this morning, he talks about reasonable, if the code is reasonable, if you can reason about it. It's difficult to follow code that's structured like this. So Polyrichus, the ancient philosopher, again says you should refactor your nested conditional to guard clauses. So if you do that, the code ends up looking like this. And this is the same code, it has the same externally observable behavior, but it's much smaller, it's much easier to reason about, and that means it's also easier to change. But it does the same thing. Yet I would argue that this is superior to the other one because it facilitates change, which the other one really doesn't. And that makes the entire organism much more fit for changes in its environment. So form matters. If we don't think about how we structure our code, it's going to have an impact on the software we're going to be able to deliver in the future. I want to show you a couple of examples of just how bad it can be. So a couple of years ago, I was fortunate enough that I was contacted by a client that wanted me to help them with some of their legacy code. And they were kind enough to actually let me look at some of their code. And I looked through it and I said, this is great. I can help you with this, but also, can I use this for instructional purposes? I promise, I'm going to rename all the variables, I'm going to rename all the methods, I'm going to rename all the classes, I'm going to sort of obscure things in all sorts of ways, but can I do that? Would you be okay with that? And they say, yeah, okay, please go ahead, do that. So that's what we're looking at here. So this is sort of like real legacy code, or rather my imitation of their real legacy code. I just took and renamed all the things. And as I was looking through the code, all sorts of things started to appear to me as being odd. And by the way, don't worry that things are just moving off to the right and continuing on down screen. That's really not the point here. But if you look at the upper left-hand quarter of the screen, you might notice that there's this curly bracket that's just seemed like it's sitting there and not really doing anything. And I was wondering, why is that curly bracket there? There was, a closing curly bracket as well. So the code compiled and it worked well enough. But I thought, that's odd, why is that curly bracket there? And I thought, I guess I know what happened. Probably once upon a time there was some sort of conditional. So maybe the code looked like this. And then, you know, sometime later on, the developers decided that, oh, the thing that is actually inside of that block of code, inside of that, you know, conditional, that should actually always run. So they just deleted the if statement, but forgot to delete the curly bracket and just left it there, and still compiled it and worked, and that's how that ended up looking like that. That was my theory. And that lasted all of like 5 minutes, because then I looked, you know, further on in the code, and I noticed that this seemed to be quite a frequent pattern in the code, that you had these curly brackets that were just sitting there. And sometimes they were even nested, so you had curly brackets that seemed to do nothing within other curly brackets that seemed to do nothing. So I was a little bit mystified there, so I had a chance to go and talk to the people afterwards, and I said, you know, why is that? You know, why do you have these curly brackets? Oh, they said, yeah, it's because those curly brackets introduce a variable scope. So, you know, within that scope, something like HFC factor and bonus key and order key, they're now in that scope, and when the closing curly bracket closes, they're out of scope, and that means further on down in the same method, you can introduce those variables again. You might even decide to have a new variable called HFC factor, but have it a bool or an int instead of a decimal, and that would actually work. And that's quite appalling. You know, the methods were like 750 lines long, so that's why they sort of decided to do it in that way. And I'm not sure that, you know, someone just decided to be evil, but this is not a form that makes it easy to make changes. Well, you can make lots of changes, but it's going to be, you know, it's going to be like blind evolution. You know, if you just try to make changes to this, most of the software systems will not actually work. It will not be fit for the real world. So, you know, code structured like this matters in the sense that it's going to slow you down quite massively. This is called legacy code for a reason, or technical debt. So here's another example. I want, by the way, also to remind you that Copenhagen, again, in this morning, if you were there, he showed you the example of the heartbleed bug, where there was basically a matter of indentation that made the code difficult to read. And here's one in the same family. So if you look at this, consider if you can tell what's odd about this. Now, I don't want you to actually shout it to me or anything, but just take a moment to look at this code and see if you can find anything strange about it. But I'll help you out here. So one way we can analyze, or we can try to find out what's odd here, is that we can see if the brackets are balanced. And the way that, if you want to know that, you can start with the counter 0, and every time you encounter an opening bracket, you just increment your counter, and every time you encounter a closing bracket, you decrement it. And if you start at 0, you should, you know, end at 0. So let's do that. We'll start at 0, and the first opening bracket we find is between calculate and post state. So that's 1. And then there's another opening bracket all the way to the right, so that's 2. And then on the next line, almost all the way to the left, there's one, you know, after the fat arrow, so that's 3. And then on the next line again, you know, between contains and cart, there's another opening bracket there. So that's 4. And then we start to encounter the closing brackets. So there's two more just to the right of the opening one there. So that's 3, 2, and then there's one more towards the end there. That's 1, you know, all the way to the end, just before the semicolon. We should have been at 0, but we're at 1. It seems like there's missing a closing bracket there. So you say, okay, so this is C# code. Obviously, this is not going to compile, but it does. Okay, so what's going on here? Now, I'm not in the habit of just arbitrarily deciding to count brackets when I'm looking at code. But what I do is that I do a lot of programming in F#, and F#, just like Python, has significant white space. And when you're working in a language that has significant white space, it's a good idea to turn on, you know, show the white space in your editor. So I have my editor constantly set up to always show the white space, and it does that for C# code as well. And when you have that, the code actually looks like this. So all the small dots there, they're space characters. And you'll probably notice there that there's just those space characters running off to the right. And you go, gee, I wonder what's going on, out there towards the right of the screen. So you scroll horizontally. I hate horizontal scrolling. And then, out beyond even the largest screen, there sits another Boolean expression and the closing bracket. And you're just like, that is pure evil. You could have looked at this code for hours trying to understand why it doesn't do what it is that you think it's doing, and it's because someone hit something out at character 500 or something like that. It's crazy. And I don't think they did it on purpose. I think there was some sort of accident that caused this to happen. But this is an honest to God replication or imitation of what that code actually looked like. So this is going to slow you down dramatically if you have code that looks like this. Form matters. So it's easy enough to point fingers at other people's bad code. And we can learn from it, that's fine, but we also need to figure out, okay, so one thing is that other people write bad code, but I probably write bad code also. How do I prevent that from happening? One of the points that Joseph Yoder and Brian Foote makes in this article called The Selfless Class is that they say, if you have code that is easy to understand and easy to change, it will be changed because it's easy to change. And most of the changes that it will be subjected to will make it worse. So they're sort of arguing from this perspective that, perfect, malleable, reasonable code is an unstable equilibrium. It's sort of going to slide down and code rot is going to set in eventually. So we need to make an active effort in order to prevent code from rotting. We need to take a stance and be sure that we attain good form. Now the question is though, how do you attain good form? So lots of people want to figure out if there's some way, some process they can follow, or if there's some way they can measure whether their code actually has good form. I'm not saying there isn't, but for the purpose of my further argument here, I'm just going to pretend that there is no such thing. I often encounter, particularly in the last decade, and particularly among people who do a lot of thinking about agile software development, I often run into this argument that what really matters is whether you can put software in production. So they often come with the following argument that says, well, if it's not in production, you can have the most beautiful code you've ever written, but if it's not actually in production, it's not providing value. So who cares about your beautiful code if it's not in production? And I have no problem with that. I think it is a perfectly valid argument, and there's a book called Accelerate that documents to a quite boring degree just how true this probably is. Teams that can put new code into production multiple times a day vastly outperforms teams that can only deploy new code every 6 months. So it's true that code does not provide value if it's not in production, but sometimes people make the oddest logical leaps from a thing like that. So I often get sort of the argument then that any code that runs in production is valuable, which is absolutely not the same thing. That does not follow logically from this at all. Is it providing value if it's in production? And that is not clear at all. First of all, we don't know what value is. I would argue that we don't know this. Now, another ancient insight we might, just revisit here is this doesn't have to come from the Greeks. This can basically come from any ancient cultures. Think about love. Think about someone you love dearly. I hope that you have either a spouse or a child or a parent or grandchild or grandparent or girlfriend, boyfriend, or good friend or whatever, someone else in your life that you love really much. Think about that person or those people and then measure that love. And it just doesn't make any sense. You can't measure love, and we've known this for thousands of years, so that's not a profound insight at all. But what I think is interesting is that we make most of our most impactful life decisions based on love. We decide to get married. We decide to have children. Sometimes we decide to get divorced because we don't like love the other person anymore, and things like that. We sacrifice ourselves for the people we love. We make life-altering decisions based on something that we cannot measure. So we should not forget that lesson just because we're now working in business and we're writing code. Because again, with programming, we often get this idea that it seems so quantifiable somehow, because everything is sort of like true or false, but it's not really like that. It's really intangible, and we can't really forget, or we shouldn't allow ourselves to forget that there's a lot of things going on in software development that's actually not measurable, and technical debt is one of them. So I would argue this: you don't know the value of your software. And I get into discussions with particular project managers quite often about this, and they say, yeah, I do. I'm just going to look at the revenue my software generates, and I'm just going to subtract my cost, and that's my value. What do you say to that? And I'm saying that is a very one-dimensional view of your software and the value and so on. And I understand why people do this, but I think again we need to learn from the ancient Greek. So around the same time as Plato ran around, there was this guy called Herodotus, and he's considered to be the first historian. And he has this quote, or there's this Herodotus quote: "Call no man happy till he dies." Now, Herodotus wrote stories about wars and kings in ancient Greece. Like he lived in around 400 BC, 450 BC. And again, if you think about movies about the ancient Greeks, some of you have probably seen 300. This story. This is Sparta. Everyone knows that quote. That's the story about King Leonidas and the Battle of Thermopylae. But Herodotus was his first historian who actually wrote about those events. So that's why we actually know about those stories. And one thing that seems like a recurring thing that happens again in these things, he wrote about kings. And kings were really special individuals back then. A king would have untold riches, would have access to luxuries that normal people would not have access to. Kings would have access to women, and I'm sorry, there's parts of this talk that's a little bit sexist, but it's just like because ancient Greece was really sexist. I'm basically just trying to tell how it was. So a rich king would have access to women, so he'd probably have lots of sons and lots of daughters and a nice wife and some concubines, and being able to command armies, and he'd have slaves and all of these things. And normal Greeks would look upon a king like that and say, what a happy man. But what sometimes happens, and Herodotus' stories, there's more than one example of this. What sometimes happens, kings make war on other kings, and sometimes kings are defeated. And what happens to a defeated king? Well, more than once in these stories, what the conquerors do is that they gather the king and the king's family around, and then, while the king is still alive, they kill all the sons, in front of the king, probably in gruesome ways, and they rape all the daughters and sell them into slavery, because that's a fate even worse than death. They may do the same with the wife and the concubines, and once they're done with his entire family, and it goes without saying that all his riches and all his luxuries are taken away from him, then they torture him to death. And then the question is, such a man, would you call that man a happy man? He had all of those things before he died, but the end is so gruesome, and it was all for naught. And you'd say, well, was that a happy man? And Herodotus' argument is that no. You cannot determine whether a man was happy until the life is actually over. Then you can make a judgment and say, oh, that actually turned out pretty well. Or, yeah, that it looked good at the beginning, but it turned out really gruesome towards the end. So, nah, not really. And I think we should have the same perspective on software, because again, I'm running into these people who sort of just, create a timeline of their profits, and they say, hey, look at this, this is going great, and today was better than yesterday, and I'm sure tomorrow is going to be better than today, because the extrapolation looks like that's going to be the case. And sometimes that turns out to be true, but sometimes something else happens, and you might have some catastrophic event that just invalidates all the value that you built up, up until then. And I've seen that happen multiple times, and the public have seen this happen as well. I'm fairly sure that the people who decided to do this, emission cheating software in the Volkswagen cars, they thought it was a pretty good idea. They cheated the American authorities for years, and during all of those years, I'm sure they were patting themselves on the back and saying, what value this software creates. This is great. Until one day they were found out, and now some of these people are in jail, and they're probably thinking, yeah, maybe it wasn't so great after all. So I've seen this happen more than once. Sometimes it's an external event, like you're cheating and you were found out, but it might not be that you're actually knowing this. I had a client a few years ago that contacted me because they were a company that had been running for more than a decade, and they made a profit every year. So quite a successful company, and they were now looking at expanding into a new market. They had a really great market opportunity, but they needed to make some changes to the software in order to expand into that new market. And they told me about what it was that they were doing, and I said to them, wow, you're looking at revenue of €1 billion, because I knew the market they were about to engage in. And the CEO looked at me and said, yeah, that's what we're looking at. And I said, that's great, okay. And then I asked for a little bit more than I usually do. But apart from that, so we actually tried to get this to work, but it turned out that even though they had this software that had sustained the business for more than a decade, we couldn't change it. We couldn't change it enough so that we could actually move in the strategic direction that the CEO wanted us to move. And eventually we failed. And I talked to the CEO half a year later, and we were just sitting. I regularly talk to him, and we were just sitting over a cup of coffee, and he looks at me and says, "I knew we had technical debt, but I had no idea it was this bad." And I didn't know either, because I was just brought in to help him, but it was really bad. And this company missed a €1 billion opportunity and basically ended up being bought by its competitor because it couldn't execute on its strategic objectives, because the code was not in a way that enabled you to go in the right direction. It was the shape of the code that caused all the problems. So you might think you have something good, but there might be things you're not aware of. So you can't really don't deceive yourself into thinking that you can measure your way out of problems, because you probably can't. So if you can't measure your way towards attaining good form, and again, there are things you can do, but let's just pretend that you can't. If you can't do that, then how do you attain good form? How do you make sure that the code is in a state that enables further development, that you can make changes and be confident that the changes you're making are actually good? And this is again where we need to look up and forget that we're engineers. So it's fine sometimes just think about ourselves as engineers. That's fine, but sometimes forget about that. Exercise taste. Use some subjective judgment. Try to figure out, what's the best implementation or the best way of expressing a particular problem. If you look at something like this, for example, you'd say, well, is this the best implementation of the Fizzbus kata in C# you've ever seen? And you say, well, that's pretty good. And to be honest, it is pretty good, because the Fizzbus kata is such a ridiculously simple problem that this is good enough. But let's pretend, just for the sake of argument, let's pretend that the Fizzbus problem is more difficult, and it's not written in stone, so there might be changes coming along the way, and we want to write the code in a better way. So if we pretend this is harder than it actually is, what could we do better? Well, one thing that's the problem with this is that we have, a mix of concerns here. So we have some business decision logic, deciding what to write, is intermixed with, user interface stuff, actually writing to the console. And this is not testable code. We can't test the code. So you'd say, well, okay, so one way to get around this problem is that we could separate the concerns. So we have a function called convert that takes an integer and returns a string. And then we have a main method that just composes, just enumerates from 1 to 100, translates all the numbers with the convert function, and then writes the resulting string on the console. I've done this exercise quite a few times, and trust me, that convert function is trivial to unit test. So this might be better. I'm not saying that it is better. It is better in a context. Exercise some subjective judgment. Try it out and figure out which one you prefer. I'm not saying there's a hard rule here. It's up to you to figure out what's the best way to solve a particular problem. So is this the best that we can do then? I think we can do something else. Now, if you think about the way that the Fizzbus problem is normally described, it goes something like this. So the problem is, the description is, write the numbers from 1 to 100. If the number is, there are special rules. If the number is a multiple of 3, then write fizz. If the number is a multiple of 5, then write buzz. And if the number is a multiple of both 3 and 5, then write Fizzbus. Okay, so notice that there is this phrase that is commonly occurring in this problem description, and that is a multiple of. And it's not there on the screen. Also, on the screen there's this magic number 15, which is not in the problem description at all. So we're not actually letting the code express the solution in terms of the ubiquitous language of the problem. So if you're into domain-driven design, you'd say, we should adopt the ubiquitous language of the domain, and it talks about is a multiple of, and it talks about multiple of 3 and 5, and not of 15. So we should express the code that way. So we can do that. So we might do something like this, where we say, okay, so we have a little helper function there called is a multiple of, and then in the code, the convert function there, we say if I is a multiple of 3 and I is a multiple of 5, then return Fizzbus, and so on. So we've now avoided this magical constant 15 that was not in the problem description, and we've actually used the language of the domain. Is this better? Well, it's your subjective judgment. It's up to you to exercise taste. But the point here is more that I don't think you should just reach for the first solution that you have. The first solution that I showed you gets the job done in the sense that this is code that the computer can understand. But you have to, or let's put it another way. I've met lots of programmers that as soon as the code does something the computer can understand, they stop. Say, that's good enough. It's not. You have to keep on thinking about, can I improve the code so that other humans can understand it better? And that might not mean leaving it as just the bare minimum. You might actually want to do some embellishment like this. Or you might decide to write it in a completely different language. So you could write it in F# instead of C#, or you could write it in Haskell if you wanted to do that. So, but this still follows the same structure. This is still, it's multiple of, and there's a convert function and so on. So it's not that it's really a radically or a structurally different approach to the problem. So I think you have the best. You can make the best choices if you have options. So it pays to have options. And I want to illustrate that we can actually approach this problem in some really different ways than this one shows. And I want your participation in demonstrating that. So don't worry, I don't want any of you up here on stage with me, but I want you to participate in what comes next, okay? So this is a demonstration of a radically different way of solving the Fizzbus kata. So first of all, I want, in a little while, but I'm giving you some instructions first. So all the ones here in the middle of the theater. Now, in a little while, I'm going to count down 3, 2, 1, 0, and then these numbers are going to start appearing on the screen. And as they appear, I want you, all the people in the middle, only in the middle of the theater, I want you to whisper the numbers. In English, please, even though I know that you speak Romanian. So it'll go something like 1, 2, 3, 4. So as you notice, I want you to sort of whisper very loudly, and there's a reason for that. So don't go like 1, 2, 3. so no one can hear. We still need to be able to hear you, but it needs to be sort of like a theater whisper. So only the people in the middle, I'll have something to do for those of you in the wings in just a moment, so don't despair. You'll all get involved in this, okay? So are you ready? All right, I'll take that as a yes. Okay, let's go. Okay, not yet. Okay, now. 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, you were so good, thank you. That was great. Cool. All right, so I'll get back to you in a moment. So don't forget what you just learned here, because you have to do it again. But the reason why I wanted you to do this is because producing a sequence of numbers in most languages is trivial. It's also trivial in Haskell. We'll just do it like this. So whenever you see square brackets in Haskell, that's a list of things. So 1.100, that just means the list from numbers from 1 to 100. That's called a list comprehension. Lots of languages have that. And then show just means turn them into strings. So this is basically just the list of all the strings, 1, 2, 3, 4, up to 100. So that's basically what I had you whisper, and we can express that in code like this. Now, I want the people on the left-hand side of the theater now to, do this. This is a little bit harder, but because you notice it says silence, silence, fizz. Silence, silence, fizz. So whenever it says silence, guess what you have to say? Nothing, that's right. And when it says fizz, I don't want you to whisper fizz, I want you to shout fizz. Okay? So it'll go something like fizz! Fizz! Alright, I'm sure you can do that. Okay, are you ready? So we'll go 3, 2. Fizz! 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 All right, you're so good at this. Okay, now the reason is, again, this is trivial to express in Haskell. So we just start with a little list of 3 elements. Nothing, nothing, just fizz. So nothing is just the same as silence, and just fizz is just to distinguish from nothing. So between those 2 square brackets there, we have nothing, nothing, just fizz. That's a little list with only 3 elements. But then it says cycle in front of it, and cycle is just a function that makes a list repeat infinitely. So basically what we have here is just a list that just goes, nothing, nothing, just fizz, nothing, nothing, just fizz, nothing, nothing, just fizz, and it just keeps on going until we stop it. So that's pretty easy to do as well. So you can probably guess what's coming to you, right? All right, so yours is a little bit harder again, because you have to go silence 4 times and then a buzz, and silence 4 times and then a buzz. But I'm sure you can do it, because you heard how well the other people do it. And just like the fizz people on the left-hand side in the right wing here, I want you to shout a buzz when it's your turn to say buzz. Just really shout it as loud as you'd like to do. All right, are you ready? Well, let's go. Okay. Buzz! 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 Right, I think we're ready. Okay. Again, the reason why I'm doing this is, again, this is trivial to express in Haskell. We just say, okay, here's a list of 5 elements, nothing, 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 just buzz, and then we just cycle that infinitely as well, and we just have this list. So what we now need to do is somehow figuring out how to combine all of those things. So we're going to do this by basically just starting having 2 waveforms that can resonate with each other. So you can see what I want. So don't worry about this in the middle. I'll get back to you in a moment, but I'll need you to stay silent a little bit longer, even though I know it's hard because it's the other people having all the fun here. But I want you, on the right-hand side here to do what you did before, silence, silence, fizz, and don't really worry about what the other people are saying. And over here, I obviously want you to go, silence, 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 buzz, just like you did before. So we'll do it together, and don't worry too much about what the other people are doing. Just follow the screen here, and everything's going to be cool. All right, let's go. Peace. Buzz. Peace. Peace. All right. Okay. So we almost got it, but I think it's still pretty good. But you'll notice that that when we reach the number, the 15th iteration, we say fizz and buzz at the same time. So we have this resonance effect going on. So it's almost like you have two waveforms that go on different frequencies, but sometimes the frequencies actually collide, and you have this amplification going on. That's called resonance. This is not too hard to express in Haskell. So in Haskell we have this thing called the monoidal concatenation operator, and this would actually enable us to combine those two streams of things together. And if we do that, I use something called zip width to do that. So I take all the fizzes and all the buzzes, those are those two infinite streams, and I'm just combine them, I'm sort of smash them together. I'm letting them run at the same time, if you will, just like I did with you. And what I get there is a list that basically looks like this. So it says nothing, nothing, just fizz, nothing, just buzz, and so on. And you notice the 15th element there, it actually says fizz buzz because it concatenates things together. So that seems pretty promising. So now we have the fizz buzzes. Now we just need to figure out, okay, what about the numbers? So we're actually now going to try all of this together. And there's a reason why I want you to whisper. So when we now do this all together, the fizzes over there and the buzzes over there, you should just do as you did the last time, but together. And in the middle, you should also just whisper the numbers just like you did before. And you don't have to be silenced even though when you reach 3, the other ones are going to say fizz. Just whisper 3 anyway, and when you reach 5, just whisper 5 anyway, even though you know that someone else is going to shout. And just keep the steady rhythm. You're sort of like the backbone of all of this, okay? So, all together now. 3, 2, 1. That was beautiful. I was really hoping this would work, and unfortunately it did. So the reason why I wanted you to whisper was that you're sort of the backbone. You're always there, but I also wanted to let the fizzes and the buzzes take precedence, so that if there's a fizz or if there's a buzz or a fizz buzz, that sort of just drowns you out, but you're always there. So that's the last way we sort of need to figure out how to smash those things together. And we can do that with another zip width. So from maybe is basically just saying, well, if there's a fizz or a buzz, I'm going to take that. But if there's nothing, I'm just going to pick from the numbers instead. And that produces a series of strings that go 1, 2, fizz, 4, buzz, fizz, 7, 8, fizz, and so on. So now you basically have a completely different solution to the fizz-buzz Carter that is based on sort of like a rhythm and a resonance pattern and some interesting mathematical properties as well. And that's a completely different solution to the problem. And I like having very different solutions to the same problem because that gives me alternatives, and now I can pick the one that I think is best. Now this is mostly for fun, right? The other one is probably easier to understand, but I think it's nice to be aware of options. So this one was sort of like a little bit musical, or at least it was sort of it was based on rhythms and resonance patterns. So I want to. Since I was talking about taste, and we already had a previous speaker talking about art and programming, I want to show you another approach to the Fizzbuzz Carter, and then we can call it a day. Midnight takes your heart and your soul. While your heart is as high as your soul, put your heart without your soul into your heart. Give back your heart. I'm going to spare you for the rest of it. But what I just read for you was a function definition of the modulo function. This is code. It looks like a poem. It's actually supposed to look like lyrics for a rock song. But it is actually a programming language. It's a programming language called Rockstar. And it started with a tweet from Paul Stovell. To really confuse recruiters, someone should make a programming language called Rockstar. And as you can tell, it got quite a bit of likes and retweets all by itself. But then there's this guy in London called Dylan Beattie, who's not only a programmer but also a musician, and he saw that tweet and he was having a couple of beers at a bar someday and Friday evening, and he thought to himself, well, you know, someone should actually sit down and write a spec for this rockstar language, and that someone is probably me. So he did that and introduced that to the world. So a proposal for a Turing-complete programming language in which you can write programs that are also 1980s power ballads. So he's very much into, he's thinking about, bands like Bon Jovi and things like that. So that's why this is the Fizzbus Carter written in Rockstar. You can actually take this, there's a little bit more to it here, but you can actually take this and put it into an interpreter. There's an online interpreter. If you go to codewithrockstar.com, there's actually an online interpreter, and you can take this and paste it into the interpreter and say rock, because you don't say go or execute, you say rock. And then it's actually going to print out, the Fizzbus numbers and fizzes and buses, just like everything else was supposed to do. So I thought that was interesting as a closing, idea to say, well, there's quite a lot of, we have, quite a wide variety, and we have quite an opportunity to express ourselves, and I think we should, take advantage of that opportunity. We can almost think about code as a poem, and we've learned from the Greek that, the poetic form might actually be what sustained those epic poems all along. They might not have been around today were it not for the poetic form. So the form really matters. In general, if you have some content you want to perpetuate, the form is the vehicle, the transport mechanism for that content. And if you're not aware of the form, the content is going to wither away and die. So if you want to produce software that works not only today, but also tomorrow, and the next year, and generally in the future, that can evolve with changing requirements and go after new opportunities, you can't do that if you don't think about the code today. So you need to think about that, keep technical debt, in check. You can't measure it, call no man happy until he dies, but you can still know that it's there. Thank you very much.
Thank you, Mark.
I want to say one thing though. I'll be out in the booth at the Today's magazine. We have a few, copies of my book, Dependency Injection, Principles, Patterns, and other things. So we can give those away if you come and want to talk to me, and you can, ask me a good question or something. I decide who gets the books. But I'll be happy to talk to you. But we'll do it out at the booth. So thanks for coming, and I hope you have a good day today.
Thank you very much. Thank you for your inspiring talk. Thank you so much.